Okay, in this video, we're going to take a look at shortcuts to finding derivatives. So recall first, what is the definition of the derivative? It is this fancy limit. We have some notation f prime of x. Man, that limit, really annoying. Oh, I guess I kind of spoiled it. So evaluating this limit is tedious, annoying, frustrating, and definitely not cool, bro. So the question we have, can we come up with shortcuts? Is there a more convenient way of doing all of this without doing the whole limit process and a bunch of algebraic manipulation? And the answer to that is yes. So let's look at just your standard parabola, x squared. If we were to apply the limit definition, then you would get x plus h all squared minus x squared over h, taking that limit as h goes to 0. So obviously we have a problem of division by 0, so we got to do some algebra trickery. If you FOIL that numerator, it looks like you're going to get an x squared and a minus x squared, and those are going to cancel. And then it looks like the numerator has a common factor of an h that you can pull out and then cancel with the factor of h in the denominator. So then you get 2x plus h over 1. And now as h goes to 0, you're left with 2x. Keep in mind, h is the thing that we're taking the limit with respect to. We are not really considering as x goes in any direction. So let's take a look at what we started with and what we ended with. Let's compare x squared with 2x. So x squared was my original function. 2x was the result after performing that specific limiting process, the limit of that difference quotient. Let's compare and contrast. So I had a 2 as an exponent. Now I have a 2 as a coefficient. Also looks like my exponent 2 is now a 1. So there's a pattern here, and this would have worked out if we had x cubed, x to the fourth, etc. So this is called the power rule. If my function looks like x to the n, where n is rational, so it cannot be pi or e or square root of 2, as long as it's a rational number, my derivative, in order to find it, I can just move my exponent to be a coefficient, and then where my exponent was, I just subtract a 1. So for example, if I had a function x to the sixth, to find my derivative, that 6 would then be a coefficient, and then the exponent of a 6 would reduce down to a 5. So it looks like a 6th degree polynomial would reduce to degree 5 polynomial. So that's our first rule. We're going to be using a whole bunch throughout the year. Next, let's take a look at the constant rule. So let's say I have a constant function, y equals c. That's just a horizontal line. So derivative is all about telling us the change at specific points. Horizontal lines don't have any change. Their slope is 0 everywhere. So that's kind of a nice little trick. If I have a constant function, my derivative is automatically going to be 0. So if I have this really complicated looking thing, pi cubed times root 5 all over e to the 2/3, I don't see any x there. I don't see any variable. This is a function f, which is supposed to depend on the variable x. There are no x's. So this is some bizarre constant. I could type that into my calculator and get some number. All that matters is it is a constant. It is not a variable, which means its derivative is automatically 0. Here are some trig function rules, and we will prove these in class. So if you have sine of x, its derivative ends up being cosine of x. Very interesting. And if you start with cosine x, its derivative actually ends up to be minus sine of x, and we'll talk about why that is when we prove these in class. So just some more properties that we can use with the derivative. Oh wow, I even spelled that wrong. Derivative, the derivative. So properties that we can apply. The derivative is a limit. So a lot of the properties that we have with limits should also apply to derivatives. The only caveat is we're not just taking a limit of any old function, we're taking the limit of the difference quotient. So it's slightly different. So not all of the same things apply, but some of them should. So before we get into them, just to make sure we remember some notation of derivatives. So f prime of x, that's what we call the derivative. You could also write this as dy dx. This is called Leibniz notation, named after the mathematician and philosopher Leibniz. Should Google Leibniz versus Newton. Very big math drama back in the day. Another way you could write that is d dx of f of x, or for that matter, d dx of y. Another way you could write the derivative as a limit. So that same limit definition, or the other limit definition that we had. The point of this is there are many ways that we can express we are taking the derivative of something. So this dy dx or the ddx notation, we're going to see quite a bit. So in these properties, they will kind of come into play here. So these first three properties basically tell us kind of the same thing that limit properties tell us. If I have two functions adding or subtracting, or if I have a constant times a function, I can actually just perform the derivative of each term. So term by term, or for that matter, with a constant, I can factor that constant out, perform the derivative, and then multiply it back in afterwards. So you might also think of some other limit properties, like with multiples, or I should say a product and a quotient. So you might be thinking, oh, well, maybe I could also do the derivative of a product and like differentiate the first factor function and then the second one and then multiply together. And for that matter, why would I stop there? I should also be able to take the derivative of a quotient by doing the derivative of the numerator function and then dividing by the derivative of the denominator function. Unfortunately, no, these do not work. There are reasons for that. We're going to come up with some rules when we do have products and quotients. But for now, be wary or be careful, rather, not to fall into the trap of doing this. So that should do it for now, and that should give you plenty of information to answer all of the questions on Schoology.